Hi, my name is Tesla Bensom, and I studied the analysis of low temperature hydrogen plasmas for carbon-free reduction of iron oxides. Trust me, I know it's a mouthful of a title. So, I studied in the city of Dortmund in Germany. I studied at the Technical University of Dortmund, and just for context, I am a mechanical engineering and a German major. I absolutely loved Dortmund as a city. It's actually one of the greenest cities in Germany, and so it has a lot of just beautiful scenery everywhere you go. There's trees, there's parks, the architecture itself is beautiful. Dortmund is an absolutely fantastic city, and I would recommend it to anybody that's planning on going to Germany, especially engineering majors, because the technical university has a lot of really, really good connections, and it has so many good opportunities. It is a great place to go study. But what I actually studied, to get a little bit into that, is with the iron reductions and whatnot, the industry sector in which iron reductions kind of lies, as of 2019, was responsible for about 24% of global greenhouse gas emissions. But in metal reductions, that's responsible for like 25% of the industry sector of the world, which makes metal reductions responsible for like 6% of global greenhouse gas emissions, which is like a lot. This is because it is done using either carbon or carbon monoxide. And in using this carbon monoxide, we have byproducts of carbon monoxide or carbon dioxide, which are the greatest contributors to these greenhouse gas emissions. The thing about metal oxide reductions is it can be done with dihydrogen. And so when it's done with dihydrogen, our only byproduct that we actually have is water. So the sort of gas you see coming out of this plant, that's not any sort of Verschmutzung, the German word. That's not any sort of like air pollutant. That's actually just water going back into our air. And so when this is done, though, it's done using a plasma. And what you're seeing here is just a drawing of the plasma chamber that I actually used in my research. And it was so much fun to learn how to use this. And when I was working, I worked with a mixture of argon gas and hydrogen gas. And with these two combined, I was able to create this kind of pinkish gas that you saw on the first slide. And when this was being used, as shown here, this is more of a 3D view of the dual inductive coupled plasma chamber that I used. You can see that it kind of created this entire gas that the iron was actually surrounded by. As shown on the right, that is the apparatus that actually held the iron oxide samples that I was working with. The samples themselves would be placed in section 3 of the sample holder, and the shutter on top, which is part 1, was just a shutter to close over above, and that helped me control the exact, like, to the second amount of time that our iron oxides were being handled. And some of our most interesting findings from this were that when we used more and more percentage of dihydrogen in our, plasma percentages between hydrogen and argon, we found that we had to use a lower gas temperature to get about the same results, which was very interesting. And we did also find that the oxygen percentages of our elements were lowering consistently when we used more and more hydrogen. Now, in my research, I was only able to get up to about 37% hydrogen, but I would have loved to go further to see what happens if we use 80%, what happens if we use 90, 100, et cetera, et cetera. And if I ever got the opportunity, I would absolutely go back and go and just try this again? And I'm really excited to go into further detail with this with the IGP Summit, and I'm happy to answer any questions at the summit itself. And I honestly, I can't wait to talk to all of y'all. Yep. So I hope y'all have a nice evening, and I will see you on November 14th. Bye.